Good morning, everyone. First of all, thanks for everyone that made it today. Saturday morning, it's probably tough for most people. Actually, I came in, I was thinking, when I first saw the schedule at 9 a.m., I was like, oh, this is going to be nice. I can go in, get my stuff done in and out, and then actually enjoy the rest of the day. But kind of backfired me on last night where it's like, oh, it's kind of like going to the airport. I'm like, oh, man, instead of packing, I'm busy working on my slides and everything. And now, like, I'm rushing in, hoping, like, I'm not going to miss my talk. But, yeah. And I promise it won't be about AI, and it's something even scary. Linux boot time. So this is my name is Ed Chong. This is my fourth year at Red Hat, and prior to that I've been working in the perf and scale for automotive, and prior to that I was at Siemens working on their fire safety division, working on firmware for their fire panels and smoke detectors and everything fire related. And this is a continuation of last year's talk where I co-presented with Brian Maisney and Eric Curtin. It's pretty much for taking the stuff we learned from last time and applying it to a new platform and finding some surprises along the way. So why speed up boot time? Because it boils down to wall clock time, because that's what the user experiences when they first step in the car. So and anything that slows that down is noticeable. So if you imagine if you're sitting in a car and you're waiting for 30 seconds for anything to react to like respond, like it'll feel broken. And then there's a couple of pictures here. These are kind of like the standards. Like usually it's like 2 seconds, and the big one is the seatbelt chime and the rear view camera. So I like to think of the boot times like there's two worlds. Like there's the visible world. This is the stuff that we can usually see: the kernel, the init MFS, and user space. This is easily measurable using systemd analyze and journal logs. But there's also another part that these tools can't easily measure, and I call this the upside down. And this has firmware, bootloader, and early kernel. And unlike Stranger Things, there's no demogorgons. They're just firmware. And these three phases matter because systemd analyze can't measure it, and that's the only way we can get the wall clock time. And then in this slide, so connecting back what we talked before, this is the whole timeline, and with the wall clock time going from left to right. The right side is the systemd, what can be measured with systemd analyze journals, like I said before. And this portion is what we technically refer as system init, and this is everything before the kernel's timer has started. So this is where we can actually get measurable log, anything that we can't really measure. And we kind of solved this by using a system counter, an ARM called CNTVCT. And what it is as soon as the processor starts up, it starts running a count. And we kind of use that as our baseline to figure out how much time has elapsed since the system started up. And this first one, CNTVCT log, it can be installed in user space. So, but the problem is you can't distinguish what is actually firmware or bootloader, only up to the point where the kernel is actually measuring logs. So to solve that, there's what we call the firmware and bootloader, we call it the early boot. And to solve that, Eric Shanaday made some out-of-tree kernel patches that specifically patch it to read that CNTVCT counter as soon as the kernel starts. So that way we have a reference point. But the problem is out-of-tree, so it's a little more annoying to capture. So usually we prefer to use the first CNTVCT log as the first step, and then if we need to figure out that pre-kernel time, the early kernel time, that's when we kind of use it. Back when we first started, that early kernel time was hiding like 900 milliseconds. But after we did some optimization, it went down to like 50 or something. I think we explored it in that previous talk. And then what I mean by early kernel, this is when you see a log, a journal log, and it's nothing but zeros, that's what I mean by early kernel. That's before the timer started, and that's the hard part to find. So as far as the test setup goes, I'm first going to go over the physical view, and this is just the system under test. So this is, for us, automotive platforms. This will be so far it's only been AR64 systems. And then for that, we connected to a network to a sidekick. And for us, a sidekick is just any other machine that is connected to the system so that we can interact with it. So in this case, we would measure boot time. We would trigger the boot time test from the sidekick over to the system test. And for the previous platform that we were working on, this was more than enough. We didn't need any other connections. But on this new platform, we ended up having to extend it a little bit. So because that counter that I talked about earlier in the old platform, when you did a reboot on the command line inside Linux, it would reset that counter. But on this newer platform, it just kept on rolling. And so that required the ability to actually power on reset to be able to reset it. I think it's an undefined feature, so there's some people implement it differently, but so far I've only experienced 2 systems, and they all kind of act more like, or 3 systems actually, they all more act like if you do a reboot through the system, it'll keep on counting. And the next piece is the serial console. We added this in the early days just because it was more debugging, but in our previous platform, if you enable serial logging, it would add like 1 to 2 seconds to your boot time. So we disabled it from the get-go from before, so now we're reintroducing it. And because of this, we required the sidekick to be physically connected to that machine or interface with something that's physically connected to it. And then as far as the software, we're using AutoSD, and this is the upstream of Red Hat's in-vehicle OS. The idea is Red Hat provides a bunch of packages and tooling for OEM to be able to build a certified Linux for their cars. And then for the serial capture, we use Grab Serial. It's actually a pretty nifty Python tool, very minimal dependency, and it does like, I think it was actually meant for boot time, but it captures it, does the timestamps, does diffs. Like it's been perfect for what we've needed for. For the actual boot timing capture, so we made a tool called Boot Time Analysis Tools, and what it does is it combs through the systemd, dbus, journal logs, and also systemd analyze, and merges it all into one big log, so you have like a unified view of everything. And that runs on you can run it on once every boot. And then the test orchestrator. Since the boot time analysis tool you just run once, you capture, you need something to be able to reboot the system, and then capture logs and collect it. And for perf and scale, we have to do it multiple times. One sample isn't enough. We do at least 50 for like a good run. So this is the baseline measurement of the platform. You can see that it's at 34 seconds for the first time for first link to up, so that should be red. I thought I edited this. And then the time to first service is 19 seconds. And the industry standard KPI is 2 seconds. So we're like way off right now. And you can see the early boot is a huge chunk of the time, taking about like 12 seconds. So the first thing we did was, the first thing we discovered was like the platform differences between the two. In our older platform, it was just straight Android bootloader and then to Linux. In this new platform, we have chain bootloaders. We have U-boot, then goes in Grub, and then goes to AutoSD. So first thing was get some easy, low-hanging fruit. So a bunch of boot delay optimization. So if you ever gone into a U-boot system, you see hit any key to enter U-boot. There was a 3-second delay there, and there was another 2-second delay in Grub. So I figured first thing we do is to set that to 0, but it actually didn't do anything, which was kind of surprising to me. I was like, what's going on? So then next, I tried disabling it in Grub, and we actually saved 2 seconds. So there's at least some progress there. And then this is when we end up looking at serial logs, and then we can see from here where the booting automotive stream, that's the second bolded timestamp is the duration from the previous. So something in there is delaying it by 7.5 seconds. And most likely from Grub, or most likely from the U-boot side of things. But yeah, 7.6 seconds from Grub, sorry. Oh, I think I messed up these slides a little bit. Okay, sorry, I'll go this one now. So what we ended up doing was we're switching, wait, let me double check. Is that, okay, so with that, then we decided to switch gears and go to applying some of our already known optimizations. And one of them was using a minimize init RD that has nothing but the minimal set that required to boot. So the idea is to shrink it as much as we can, and then we also build in the storage drivers which added a little bit of time to kernel, but we did reduce the init MFS by 82%, so from 4.8 seconds to a little under a second. So that's one easy win. And then now the other thing was trying to figure out the grub portion of it. So we're gonna, at this point, we decided to switch to the Android boot image. And this means just getting rid of the grub and just using U-boot, booting straight to an A-boot image, which U-boot supports. And this solved most of the problems. That got reduced, the early boot got reduced from 10 seconds to 1 second, 90%. And then for the wall clock time investigation, so the initial assumption was that early boot and the system init measurements would apply to all platforms, and this ended up not being true. And then the discrepancy applied when we looked at the message for when their serial logs when their firmware says they're done loading, it says it's around 1.5 seconds, but our early boot measurements saying it's around 1 second. So this was like another thing I was getting me to scratch my head. So then afterwards, we talked to some kernel guys, and they were saying that there's 2 processors in this device. There's the main processor that runs AutoSD, and there's also 2 co-processors that start first before it. And this wasn't the case in our previous platform. There's only 1 processor that did everything, so this was another wrinkle that I didn't expect. So previous platform, like our current early boot measurements work perfectly. We were able to measure from time on, the whole system time on to load, and there was an issue. The current platform, what ends up happening is the processor on the Linux side starts somewhere somewhere after the board boots. So our early boot measurements is measuring only that portion. So there's still a bunch of time before that we have no idea what's going on there. So that is the observability gap that I've talked about. And to measure the gap, so we have this message in the logs that says starting kernel, and with the serial log, we at least know that it happens at 2.4 seconds. And we can also use our out-of-tree kernel patches to figure out when this starting kernel message happens when we read that ARM processor counter. So with that, we should be able to figure out the actual gap. And so in this case, it was about 1.4 seconds for the other processor startup. And then after that, we have like additional optimizations that we did. So that was pretty much the hard part, finding out that gap so that we have a complete picture from end to end what time it is. So from then onwards, we started applying our optimizations that we've done on the previous platform. So one of them is switching from network manager to MN state with static IP just to speed up the link is uptime. Other one was switching it from we were using a QA-based image that was more loaded for user space, so we switched to a smaller image. And then the other thing was the standard SC Linux package is huge. It's for servers. We ended up getting automotive tailored one that has a cut down version, and we reduced it by 50% the load time, so it went from 780 milliseconds to under 400. And it also had the benefit of reducing user space by 20%. So what does this look like overall? So this graph has everything from wall clock time. So that gray bar is the processor offset, is what I'm calling for whatever the extra hardware firmware time is added. The processor init is that portion that is only on the application processor, and then the kernel pretimer and the rest is the same from before. So you can see that we started out at 34 seconds and we ended up at 13 seconds. And this one does not have the automotive SC Linux policy present, so that should drop it down by another 400 milliseconds. And then just a comparison of how this current platform versus the previous platform. It's like night and day difference in performance. And the reason the terminology changed a little bit is because on the previous platform, we didn't need to do any special calculations for the time before the processor started up. And this brought up an interesting problem. With a much slower platform, you end up seeing things that you miss on a faster platform. So this is a chart that it's kind of hard to visualize, but if you imagine the left part is when all of the systemd root units are loaded to the root file system, and on the right is where the switch root is completed. So on this previous platform, that was only a 74 millisecond operation. On this new platform, it was a 560 millisecond operation. And this ended up causing problems because we were kind of using this endpoint as a proxy for when the first service would start. But on the newer platform, that was about 700 milliseconds off. So, and then we ended up figuring out that it was a call to manager deserialize in systemd, and when you switch root, it calls it, and it's a bunch of deserializing functions. And because the system, most likely because the processor is much slower, and also the I/O, I think it's eMCC storage, so it's the slower I/O speeds kind of hurts it. And then, as far as challenges, adopting new platforms. So previous assumptions don't apply. Slower platforms expose things that we don't technically never measured before. And every time we get a new platform, we have to do this all over again. So it's not so bad from vendor to if it's within the same vendor, but from different manufacturers, it's a whole different headache. And collaborating with hardware vendors to optimize firmware, that's always been a tough point. We're not we're not a big customer yet, so they have very low incentive to cooperate with us to optimize their side of things. But working on it. And then shout out to all the Red Hatters who help contribute this work. Like I only do the measurement and some of the stuff. A lot of this work is built up on all these Red Hatters work. And then references to previous DEF CON talk, with time analysis tools. Yeah, that's it. Yeah, I'm under time. Any questions?
Yeah, good talk. You said the industry KPI is 2 seconds. Does the current vendor of the platform you're working on have a Linux distribution or something that can meet that KPI?
I think they use, what do you call it? It's not full Linux, right? They use, where was it? Where was BlackBerry? QNX, right? One of those. So it's very customized, heavily stripped down Linux. We're trying to offer a Linux that everyone is familiar with. So you can use systemd, you can use your cloud tool, your normal tools. So it's more of an opinionated Linux distribution. While everyone else uses Yocto and it cuts it to the bare bones where you can't really do anything, which kind of limits us from the ability to be able to measure boot time too. So with that perspective, but at the same time, with that kind of stripped down method, you kind of use hardware to measure your boot time. Here, we're trying to make it more generic, so that makes our lives a little easier.
So the new optimized platform that you're saying has an increased boot time, the firmware boot time, right? What I was trying to understand is why are we then using the new one?
Oh, so it's just we're not switching between them. It's just that one vendor, one OEM wants this one OEM wants that one. It's just the newer one that we've tested. It's not like we're replacing anything. But that in itself is just like a intermediate hardware. Like none of the real hardware is actually available yet. So we gotta test with older platforms to be able to try to see what fixes, optimizations we can make, and hopefully when the new one actually comes out, we will actually be able to apply some or get them to make some changes on the new platform.
So at the end, you mentioned you're kind of at the mercy of the chip developer for the firmware boot speed. Does that come into consideration when you pick out your hardware, or does another team pick that and you just have to work with what you get?
We don't pick the hardware. The customer picks the hardware.
Oh, customer does. Okay, cool. Thank you.
This is where I wish we were like Tesla, where we can build our own car from the ground up, right? We control everything, right? But that's not going to happen.
You're still quite a ways off from that 2-second KPI. Do you have any thoughts on what you think might be the upper limit of what's achievable?
I think we're close with the previous platform. If we can cut down the firmware time, we might be able to get it. But even then, it's like we can probably get around like 2 seconds, like a little over 2 seconds for the application to start. After that, it's still at the mercy of the OEM to how long is their application going to start. But I'm hoping most of them are going to do suspend and resume. So that's probably like the next investigation aspect of it. It's like how long do we take to get to resume from a suspend?
And you didn't talk very much about the systemd user space end of the boot. Is that included in that KPI, or is it, is there a very specific process that, once this service starts, you can call the boot time as good enough in terms of, end user visibility?
Yep. Right now, we're kind of using it as like the first service to start. That's like the first systemd root service that can start is our kind of like baseline KPI. And then a couple other ones are like network to start. Some vendors want, most of them want very early networking because like the gear shifter is connected through Ethernet.
Thanks.